So I want to thank Tom and to thank all of you. It's really a great pleasure to be back at a live conference. So I have no random matrix theory and no numerical linear algebra. In fact, there's really a PDE talk in disguise, but it's really about optimization and what one can do with optimization. So the one-line summary is that I have a new stochastic scheme, and it's really crying out for grown-up numerical assistance. So I'll try to kind of cut down the ideas to really set it up in a way that I hope will be interesting to you guys. So what I'm really going to be doing is kind of introducing a different way of thinking about PDE problems and what I'll call hard constraint systems. And so what's the kind of problems that I'm talking about all have relaxation. So the whole goal over here is to understand an idea of relaxations better. And what I'm going to do is I'm going to kind of try to solve these PDEs using a stochastic control scheme. So the idea is going to be, well, you've got a PDE, well, you relax it, then you kind of keep adding in corrections. So it's conjugate gradient like in the sense that I'm going to be adding in corrections based on a residual. The whole point is that the corrections are going to be added in stochastically, not deterministically. So the ideas in the stock actually go back to work done by Nash in the 1950s. And the kind of strange feature of this talk is that I'm going to try to discover the physics of Nash's method by actually following his proof and in some sense fighting against his proof. So that's why the name Stochastic Nash evolution. So I want to, it's a PDE talk, but I want to introduce it to you perhaps in kind of a much simpler framework, a kind of very clean, discrete problem. So the discrete problem is the graph embedding problem. So what you assume given is a graph, so a finite set of vertices and edges. You equip every edge of this graph with a positive number, a weight. And then what you do is you try to put this graph into Euclidean space. Okay, so what I'm looking for is solutions to this system of algebraic equations. So there's a system of algebraic equations, one equation for every single edge on the graph, and you have to solve the system of algebraic equations. So the relaxation, so that would be a solution to the equation. A sub-solution to the equation would be a situation where we relax this equality to an inequality. Okay, so the game is going to be that we're going to have these sub-solutions, and then we're going to keep trying to bump up these sub-solutions. So the question that I'm going to ask is, what does a typical solution to these equations look like? So the whole goal over here for me is to kind of form a precise kind of formulation of this. So this is where the randomness is. Yeah, this slide? Yes. Okay, so this question kind of, I mean, we've had talks with a kind of theoretical CS flavor, but for me, this question actually arose in an experiment. So I feel like a bit like an aging rocker, kind of putting out my greatest hits. But this is, oh great, is this, how do I get the movie to play? Oh, okay, so this is a movie of a device that was, so what you're going to see is you're going to see this shape folding up. And the thing that you have to note is that each of those squares over there is actually about like a hair's width, 0.3 microns. And it builds itself. Okay, so these are experiments that I was involved in and kind of like building up toy models for protein folding. The thing that you have to observe to kind of connect this picture to what came before is that the faces of this polyhedron are rigid. So as it's moving around, it's actually moving through the solution space to the system of equations that I showed you earlier. So there's an underlying graph over here. The graph is this flat structure. Each of the corners of each of these faces is a vertex. You've got a bunch of edges. Each of these edges is of uniform length. It's tied together in a particular way, and it's moving around in space in a particular way. So what happens is that when you want to model these processes, so when you want to model these processes, so it could be, it's like the kind of question I was interested in is like, how does Buckminster fullerene form itself and things of that nature? So what happens is when you try to make models of these processes, you're thinking about sort of how do chemical bonds form. So you imagine, so over here, I'm trying to come up with a model where how a square linkage would form. So, I want to imagine that this guy is diffusing around, that guy is diffusing around, and then when they come together, they stick with some probability. So what you actually have to do is you have to kind of associate a natural probability to this configuration and that configuration. Which of these configurations is more likely? So this question kind of shows up. And in some sense, this question is the kind of key bottleneck, mathematical bottleneck in several models of protein folding and RNA folding and stuff like that. So to cut a long story short, what I'm going to do is I'm going to introduce an algorithm for associating probability measures to such configurations. And the way the algorithm is going to work is through relaxation. So what I'm going to do is I'm going to kind of shrink all the lengths. And then, what's going to happen is that these guys are just going to wiggle, 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 and they're going to push it, and they're going to get pushed apart. Okay, so the whole goal is to kind of figure out how to get wiggling right. And it's actually a problem of kind of finding the right model. And so what happens at the end of the day is that somehow this model is there, buried there in Nash's work, and kind of one has to kind of discover it with some care. Okay, so what's the scheme like, right? So that was sort of one part of the motivation. What I'm going to be doing is I'm a dynamicist, not an optimizer. So what I'm going to do is I'm going to write out a dynamical system for this evolution. And the dynamical system is going to involve two terms. So the first one is a subsolution. So something that is shrunk and it's going to bump up on average. This is a kind of mysterious term, and I'll try to give you intuition for it. So in some sense, the critical, it's a kind of critical insight that goes back to Nash. But what I'm going to do is I'm going to write out a coupled evolution for these two equations. Okay, coupled evolution equation for these two variables. So that guy is a vector, that guy is a matrix. That would be one way of thinking about it. Okay, so when you're deriving an equation, you need to have a sense of what the underlying principles are. So the critical principle over here is relaxation. So, it's a one-sided approximation. The other part is going to be stochastic kinematics, which I'm going to explain in just a second. This is a little bit more subtle. So in some sense, it really comes from the fact that when you're studying PD versions of this question, so that's what Nash was actually doing, you need to put in band limitations. So you want to find a principled approximation scheme for PD, but the way you want to do it is by adding in fluctuations with kind of very clear limitations on the smoothness of the fluctuations. The last part, in some sense, is where this becomes an optimization problem. So to cut a long story short, what's going to happen for me is that I'm going to have to kind of write out what a covariance kernel is. And this covariance kernel is going to require the solution of a semidefinite program. So this is how I'm going to kind of formulate a stochastic approximation scheme for this system of equations that I showed you. So what's going to happen is that this approximation scheme is really an approximation scheme in the sense that once one has got this formulation, it turns out that the convergence of the scheme is soft. So once you start with a subsolution, you will end up with at least a subsolution that's better than what you started with. It may not be a solution, and that's kind of where there's still a fair deal of hard work to do. Okay, so let me show you the idea on the I've really sunk to the simplest, to my natural level, let's say at this point. So what I'm trying to do is to embed 2 points into the line. So my graph consists of 2 points, a unit distance apart. And what I'm going to do is to show you how my scheme works on this particular simple model. Okay, so the idea is very straightforward. I kind of want to take these points and I kind of want to push them further and further apart. And so at every stage, I'm going to have a residual, and I'm going to choose a covariance kernel based upon the residual. Okay, so everything that I'm doing is stochastic. So I'm writing out an SDE. And the only catch is that I'm going to write out my SDE in a slightly different way than a standard. So typically when you write out an SDE over here, so here you've got these 2 points on the line. So you've got a covariance kernel, you've got some matrix over there that depends on your state, and you've got those noise terms. But it turns out that everything that I'm doing really just depends upon the covariance. So it really just depends upon this specific PSD matrix. So the whole goal is to find a principled choice of this PSD matrix. Okay, That's where the semi-definite programming is going to come in. So I'm going to be writing out my SDEs in this way. I mean, I don't know, this may bother Elliot, or this, this tends to bother the probabilists when I talk to them. But actually, this idea of kind of a distinction between the covariance kernel and the SDE itself, so this pleased me a bit, but this is a particular lemma in Strouk and Vardhan. So in some sense, this equation is quite fundamental. When you take a particular square root, you get an SDE, but in some sense, it is actually principled to write out the equation in that way. So at the end of the day, what I'm going to write out is just an equation which involves a covariance kernel, but also the evolving filter. Okay, so what's the kinematics? Okay, so what I'm trying to do is I'm trying to correct for a residual. And the important thing whenever you have an SDE is that the usual chain rule doesn't quite work, but what you have is also an etho correction. So if you're trying to correct the length, so what I have to do is to compute the the stochastic differential of the distance between 2 points. And when one applies etho's formula, what one sees is that there's the standard chain rule over here, so you get a kind of mean zero term, but then you get the etho correction. Okay, so the etho correction is very easy to write down. And it turns out that it's just a linear function of your covariance kernel. So you've got this 2x2 matrix. On average, the correction that you're getting to the residual is this particular term over here. Okay. So this term is going to recur in every single one of my problems. What really matters is simply the etho correction. The etho correction is going to be a linear function, or is going to be determined from the covariance kernel through a linear operation. And so, it's convenient to have notation for it. And so, when you look in LaTeX, there's a kind of finite number of symbols. So this one worked for me. So, this is going to be my diamond operator, and it's going to show up in different forms. So for example, here's how it shows up in the general graph embedding problem. So for the general graph embedding problem, what you have to do is you've got your vertex set. So your covariance kernel becomes a little bit more complicated because now you've got vectors in Q-dimensional space. You've got 2 points. So you've got a kernel of that nature. But you just have to apply the etho correction to compute the etho correction for every single edge in your graph. And what you end up with is a linear constraint for every single edge on your graph. Okay. So it's exactly the same calculation as was done before. It's just like in a slightly more complicated, slightly more complicated situation. Okay, so here's the control strategy. So the control strategy is like, in some sense, a stochastic version of what one would do with something like conjugate gradient. So you have a sub-solution. So if you've got a sub-solution, you have a residual. And what you want to do is you want to choose your covariance so that on average, you correct by the residue. So these are actually the equality constraints for a semi-definite program. Okay, so I've got a covariance tensor. So, think about PSD matrix, and you've got a linear function of your PSD matrix, and you want that to be equal to some residue. Okay, so every single one of the problems that I deal with basically always goes to the structure. You have a covariance kernel. Covariance kernel, you want to equate the covariance kernel to a residue. So the issue is that you have to make a principal choice of the covariance kernel. And unlike SDP, you actually have only the constraints of the SDP. You don't have a cost function. So the choice of the cost function was actually something that took me like 2 years to figure out. So somehow, there was a little bit of an issue over there. So, here's what it looks like in the simplest model. So in the simplest model, I'm trying to put my 2 points into the line. And so, I've got a residual over there. And so you see that you've got one equation with 3 unknowns. It's got many choices. So there are infinitely many PSD matrices that solve this equation. So the question really is, which of these is the best choice? Okay, so best over here is, can mean many things. So I'm a theorist. So for me, best really means I want to get to the core of the problem. But in a certain sense, like, best could also mean stuff, the covariance kernel that can be computed the fastest. So that's not a direction that I've gone in. That's a direction that I think is interesting because, the notion of what's best depends very much on kind of the tools and the goals that you have in mind. Okay, so, I kind of want to give you these simple examples so that you kind of see the principles in the background, but I also want to give you the general principles. So the general principles are, in some sense, standard principles associated to optimization. So, I've got constraints. If there may be no solution, it may be that there is no solution to this equation over here. In fact, in this particular version of the problem, there's actually a beautiful classical theory going back to Schoenberg, which actually underlies, a lot of the embedding theorems that began again with Bourgain in the late, I guess the late 80s. But even when your STP is infeasible, you've always got a relaxation. Okay, so the general structure of my problem is always the following. Given the residual, I always have this convex set of covariance kernels, and I need to make a principal choice of some covariance kernel from this convex set. So I'm going to call this a closure problem because there's a kind of story in about how I got involved in these problems. The story goes roughly as follows. Well, actually, no, I'll tell you the story later. Let's just think about this as I'm looking for a closed equation. So that's why it's called the closure problem. Okay, so the discrete problem doesn't quite capture the kind of depth of the PDE problem unless you add in rank restrictions. And so there are several reasons for this, but what I'm really going to do is to kind of carry a space of controls with me. And so earlier I just said, like, okay, you've got this set of possible covariance tensors, but I'm actually going to look at covariance tensors which are absolutely continuous with respect to a set of, with respect to a covariance kernel that I'm carrying with me. So this idea really is a kind of critical idea in Nash's work, and somehow it's a very reasonable idea when you come at these problems from control theory. So our unknown over here is not just a point. You really want to think about it as a Gaussian measure. So you could think about it as a cloud of points. So that's a kind of common picture when one looks at the Kalman filter. Equivalently, you could think about like the evolution equation that I'm writing out as the evolution equation for, let's say, the ellipsoid determined by this PSD kernel, an ellipsoid centered at a particular point. So one way of thinking about it is like, this is what my evolution looks like. I've got this ellipsoid, and the ellipsoids are going to get bigger and bigger, and the center of the ellipsoid is going to move, and this ellipsoid is going to get bigger and bigger. So this structure is, like, in some sense, the core structure. And to the best of my knowledge, I mean, this really just comes out of this particular work. This idea somehow is a kind of reformulation of Nash's work. Okay, so here's my evolution equation. And so the evolution equation has two parts. So I kind of need to evolve my, so there's one part of the evolution equation which describes how these ellipsoids get bigger and bigger. And there's another part of the evolution equation which is basically going to describe how these guys are jiggling around. So, this is the limitations of my graphic, my ability to do graphics with the Mac. But you really want to think about this point as kind of jiggling around and the ellipsoid getting bigger and bigger at the same time. And there's a coupling. Okay, so the coupling is kinematics. So this is always going to be a PSD matrix. So the ellipsoid getting bigger means that you've got a PSD matrix that gets somehow bigger. And the rate of growth of this PSD matrix is what's determining the covariance. Okay, so it's an equation that looks strange, but I'm going to show you how it works. And I hope as it'll become a little bit more familiar as we go along. So what I'm going to do is, so as I said, those are the constraints of the PSD, of the STP. What was missing was the cost function. And I'm going to choose this particular cost function to close my evolution. Okay, so the cost function is going to be an entropy. It's a relative entropy relative to the background. So there are several reasons for this, but let me just kind of show you at first how this works. Somehow there's a kind of spirit of physics in the background to basically close this equation. Maybe I should pause. I don't know. Yeah. Oh, that's a typo. Of course, M is L. Yes, ML. Yeah, there were other slides where the M for some reason, but I always use L, and so yeah. Okay, so we don't know how to do the numerics. So let me show you a very, very clunky numerical scheme. So the numerical scheme is discretized. So, I fix some time step and I'm going to discretize in time. And at any time step k, I'll assume given my state. So, that involves this sub-solution uk as well as this PST matrix. So given that, I compute the residual. So it's a sub-solution, so the residual is always positive. Then I have to solve a minimization problem. Okay, so I figure out how to solve this minimization problem. So I'm carrying my background with me. So the background is always part of the minimization problem. This is just a convenient way of kind of denoting the convex set over which I'm doing my optimization. And then after that, I do a Monte Carlo step. So what I do is I sample a Gaussian with that covariance, and then I update. Okay, so this is pretty much the most naive implementation of how one does the numerics. But let me show you what happens. Okay, so here's a simple example of how the scheme works. So I'm going to, pick a slightly more complicated model than the one I showed you. So I'm going to take a linear chain. So that's going to be my graph. I'm going to put it into the line. So each of these points is supposed to be a unit distance apart. But I'm just solving the system of algebraic equations. And I'm not going to assume that my solution should be one-to-one. So this is an admissible solution to my system of equations. So I've, labeled each of these points. And what's happened is that you can imagine a chain which has become folded as I go along. So the main point is that the distance between each of these vertices is equal to 1. Okay, so now I guess the movie. So let me just, so these are numerics done by my grad student. As I said, it's still clunky. So the way this is working is really forward Euler for the time step. And an off the shelf. So it turns out like minimizing von Neumann entropy is a huge problem in quantum mech. So it turns out that there's a kind of off the shelf routine for doing it. And so he's kind of calling this off the shelf routine at every single time step to do the optimization. So here's what happens. The points kind of push apart. So just kind of, it's always saying it's a subsolution, but it's kind of jiggling, 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 and moving outwards. And as time gets larger and larger, you get a solution. Okay. Is the picture clear? Like what was, so, there was a dynamical system, this guy's moving. So let me show you. So one of the interesting things about the graph embedding problem is that, there may not be a graph embedding. So for example, if you take a triangle and try to put it into the line, you're not going to get a solution. But the algorithm will always give you a principled subsolution. So let me show you how the embedding of a triangle works. So here I'm going to take an equilateral triangle and put it into three-dimensional space. And this kind of keeps jiggling outwards. So I'm actually cheating. This doesn't get to a solution at the end. This is still, so these numerics are just killing us right now. Okay, so I really need a grown-up to come in and tell me how to do the numerics. I'm completely convinced that I can show you that the equations, there's absolutely no doubt that it's correct. But nevertheless, the numerics, we don't quite know how to do. So here are some issues, right? So solving an optimization problem at each time step with this kind of off-the-shelf solver without using any of the information that you've got is clearly incredibly wasteful. Okay, so, but there are optimizers in the audience. I'm not one of them, but that's something that we need to figure out. Okay, so the other thing is that like this particular scheme, so it's not like this general idea of you've got a residual, add in fluctuations and go, should be a very, very useful idea. I haven't seen it out there. Maybe it is, but like it's just a very, very simple idea. And it's just this principled use of the etho correction. Other choices are certainly possible. So in a sense, what's complex about our method is that I'm actually doing an implicit scheme. So I'm given the residual, I'm finding the covariance by solving this optimization problem given the residue. This seems to give it stability. I mean, no theorems, but it seems to give it stability. But other choices are possible. In fact, for the embedding problems itself, the isometric embedding problem itself, I have much better results. I mean, completely different models. So the main argument I would say in favor of the model is really its theoretical consistency. So what's really, so going back to what Alan said yesterday. So I think, my main contribution over here is to find the right model. And it's a model that actually collapses a whole bunch of different equations. So the way I got into this is really as following. So, my main interest has been turbulence for about like 20 years. And about 10 years ago, there was a kind of breakthrough result in PDE theory. So these are results on kind of the existence of solutions to the Euler equations. It's the work of Delelis and Sekehidi. And somehow their very, very strange discovery was that, these results of Nash, which had kind of been buried in the 1950s, somehow came back to the fore, and they found a completely different way of solving the Euler equations. So this really blew my mind. I mean, like the Euler equations are like fluid mechanics. It's, I would say, the stuff of like applied math. Nash embedding, like, really, like, who actually knows what this stuff is about? Like, in my world, I definitely didn't. But somehow it was just one of these things. So what happened was with the embedding theorems, there's really been no, there's this absolute disconnect between, I would say, the world of the pure mathematicians, which, there's a wonderful survey in 2017, Bulletin of the AMS, papers by the best mathematicians on the Nash theorems, and the word probability theory does not appear in that volume. And turbulence, of course, you think probabilistically all the time. So, that was my secret weapon. And by cutting it down to the graph embedding problem, I really want to show you that the secret weapon is actually the right way to think about these theorems. So that's the real argument. And I think I'd like to push in that direction, give you a sense of where this is coming from in the time that remains. So one of the things is just the choice of variables. So it turns out that these variables can be interpreted in many, many different ways. So one way of thinking about it at kind of level, kind of fancier mathematical level, is that what's really going on is that I'm actually constructing a diffusion on a space of Gaussian measures. So another way of thinking about it is that what I'm really writing out is a diffusion of an affine Hilbert space. So you've got this kernel which is moving, so that kernel is actually a reproducing kernel. So there's actually a Hilbert space that you're moving, and the Hilbert space is centered at the point UT. So you're really moving this affine subspace. If you think about it physically, what's really going on over here is what I'm really doing is a very classical physical picture going back to Maxwell and somehow this idea of quasi-static equilibration of a thermal system. The key reason for choosing the entropy as my cost function is that there's a sense in which everything that I'm doing over here really kind of cuts down to Shannon's channel coding theorem. So there are other ways of closing the equations, but some hard constraint models of the kind that I chose use only the geometry. So it's a bit like doing the hard sphere gas or something like that. You want a minimal model, and the geometry kind of gives you a sort of minimal physics. The other one is that I can kind of think about these problems as there's a Bayesian integration where I think about kind of embedding as being a process of measurement. And so what I'm really doing by solving this optimization problem turns out to be a process of symmetrization. This one, let me actually show you in sort of quick pictures what Nash's theorem is about, because it's really the mysterious role of the kernel, which took me a little while to figure out, but in some sense this is analogous. I guess this is really for Percy. It's really analogous to Nash's smoothing operator. So let me just show you how that scheme that I've shown you for kind of just this discrete system, what kind of PDEs does it apply to, and how, why, in some sense, what I'm saying is that you should be able to solve PDEs numerically using only optimization techniques and through this particular schema. Okay, so here are three PDEs, which at first sight, if you look at Evans's book, for example, these PDEs have nothing to do with one another. And my claim is actually you can kind of formulate all of the PDEs together. So that, for example, is a Hamilton-Jacobi equation. So this is perhaps the least familiar to you guys. This is what the isometric embedding problem is. I'll give you a cleaner picture in just a second. And here are the Euler equations for incompressible flow. So it turns out that each of these equations has a natural notion of relaxation. So there's a notion of subsolution. And each of these PDEs, we have kind of existence theorems today that basically build solutions to these PDEs by adding in fluctuations. The problem with each of these existence theorems is that they're kind of fancy existence theorems, but nobody knows how to compute with them. So this is really a fundamental issue that I think Alan would appreciate. But for me, a fast algorithm is a proof. I mean, when you've got a fast algorithm, you can actually compute and see stuff. And that actually, I think, matters a great deal in applied math. Okay. So let me give you an illustration of this, right? So let me give you a sense of why the isometric embedding problem is so interesting. So this is the donut problem. So this is the mathematical donut. That's the kind of donut that you eat, okay? And the one way of thinking about this problem, so one way of thinking about the isometric embedding problem is that I'm looking for a map from this intrinsically defined space into R3. And what I want is that lengths that are measured over here should be exactly the same as lengths that are measured over there. What this boils down to is this quadratic equation. So that's the 2 by 2 identity. This is a matrix which is 3 by 2. So you have to solve that equation. Okay, if you solve that equation, you've basically found an isometric immersion. So here are two results on this equation. So the first result goes back to Tompkins in 1939, and it says that there are no C4 solutions to this problem. So Nash's theorem was very surprising because you think there are no solutions, but actually there are infinitely many solutions. The catch, of course, is the difference in smoothness. Okay, so this is where the kind of addition of fluctuations comes in. And so the basic idea in Nash's proof is relaxation followed by the introduction of fluctuations, not in a probabilistic sense, but in a kind of corrector sense. So this is a kind of big deal, and it's called convex integration. Intuitively, it goes something like this. So you kind of imagine just trying to put a circle into two, or a circle into 3 dimensions. So I'm sorry for kind of switching notation on you, but this is just du transpose du. It's just kind of written out in fancier language here. So you want to imagine what's happening in this iteration scheme is that you've got a subsolution, you're kind of adding in these wiggles around it. And the way Nash does it is by, so he has two, you have to use the codimension. So it's a curve sitting in R3. So you've got these 2 directions, and you kind of add in these wiggles in the normal directions. Here's what it actually looks like. This is the only computation that I'm really aware of this problem. So it's been 70 years. So these theorems have been out there, but we don't know how to see them. Okay, so we know that these are very interesting objects, but the first real sort of good computation of this is from this paper in 2012, and you see that the kind of embedding of isometric embedding torus has this kind of structure on many different scales. It turns out that this computation is really based on this convex integration idea, which goes back to Nash. Great proof, impossible to make an algorithm of it. So this was really done with very heavy computing, and really as far as I'm concerned, that's not kosher. I mean, this is a simple problem. You have to have a simple scheme for it. And so the absence of fast computations to this problem is really what got me so interested in kind of trying to kind of cut this down to the point where I could just do it in a kind of clean way. So the thing is that every single one of those PDEs that I showed you can be reformulated in exactly the same scheme. So each of these PDEs has a notion of subsolution. Each of these PDEs has a notion of a residual. Residual gives you a convex set. This becomes, of course, harder because the convex sets are now, integral kernels. It's infinite dimensional, but somehow the equation is exactly the same. So I want to compute this. I really just want to compute this. So it turns out that actually what happens is that so like the big step for me was realizing that probability theory is actually the core part of the problem. It's not something that's kind of ancillary and technical. It turns out that when you actually think about the constraints, so this is not the way numerical linear algebraists think about PSD matrices, but this is the way you should think about PSD matrices. PSD matrices describe Gaussian processes. So when I have a PSD matrix, what I really have is a random function that's living on my set. And so this set of constraints that you're getting over here is really just the correlation of the gradients. So it's a very, very natural set of constraints. And what happens in each of the problems that I'm talking about is that this is where the residual is going to sit. The residual is a very natural object in each of these problems. So for the isometric embedding problem, this ends up being the metric. For turbulence, it ends up being the Reynolds stress. And in some sense, technically, what it does is it actually clarifies somehow the kind of central lemma in Nash's work, which basically underlies all of the PDE results in this area over the past 10 years. So in particular, one of the things that does come out of the scheme at the kind of level of this structure is that what I'm really interested in is this problem. So this is kind of the problem of turbulence. So what you're interested in is building solutions to the equations of fluid mechanics that look something like this with structure and all of these scales. We know that this problem has universality. And my goal is really to join the dots between universality as studied in random matrix theory and universality in these problems. And I can join the dots, but that would be too much for talk, certainly not before lunch. So let me just close at this point by just telling you what I've done, right? So what I've done is I've kind of introduced the stochastic relaxation scheme. What it's really doing is reformulating large numbers of nonlinear PDE as a stochastic optimization problem. The stochastic optimization problem is, I hope I convinced you, reasonably clean. At each step, you have a residual. You have to kind of find a covariance tensor given this residual by solving an optimization problem. Several variants of the same basic idea are possible. Somehow I like my variant because it kind of gives you the natural physics of embedding, which in some sense has been missing. So the numerics require professional attention, so again, it's something where I would appreciate assistance. Somehow, there's been no prior attempt to address Nash's work with probabilistic techniques. And in every single example that I know of kind of work that came out of it, it provides a kind of new way of thinking about those problems. So I guess I'm exactly on time, so let me stop. So thanks for your attention. Yes.